Hi everyone, I am Madam Rosmaya. In this video, we are going to discuss on tutorial 17. We are going to divide into two parts. Part 1 is about photoelectric effect and part 2 is about work function and stopping potentials. Okay, for part 1, this is the first question. Is it possible for a beam of infrared radiation to contain greater total energy than a beam of ultraviolet radiation? And then explain your answer. Yes, the answer it is possible because the amount of energy depends on the frequency and also it depends on the number of photons. From the formula E equals to HF, energy of each photon. So we can see here we have frequency in the formula. So the energy depends on the frequency. Uh, the higher the frequency and the higher the energy of each photon will be. Okay, but a beam of lower frequency can have greater energy if it has more photons. So you can see here, this is energy of each photon. And if we have more photons, so that means the energy will be, let's say the number of n photon. So the energy will become NHF photon because this is energy of each photon. So we can see here that also, okay, go back to the previous slide, and we can also see here from this equation, so a beam of lower frequency can have greater energy if it has more photons. Okay, now we go to question 2. Okay, a metal plate is illuminated with a light of given frequency. Which of the following determine whether the electrons are emitted or not? So we have time of exposure to the light, then thermal conductivity of the metal, then the type of metal, the intensity of light, and E, the area of the plate. Then explain. So the answer is the type of molecules. So how we know this? So we refer to the uh, photoelectric equation, from Einstein photoelectric equation. So different metals have different threshold frequency from the formula of Einstein photoelectric equation. So the energy equals to maximum kinetic energy plus the work function. And the energy of this energy of photon equals to HF. So this equation comes from the principle of conservation of energy. Okay, so F is a frequency and then W is the work function. So depends on the type of the material, right? The work function. So different metals have different work function and the work function is equals to the HF node. Right? The maximum kinetic energy will become zero if the energy of a photon is equals to the work function of the metal. Okay, so that's the answer C. Now we go to question 3. When a metal surface is illuminated with a light of a given wavelength, not all of the photoelectrons are ejected at the same speed. So explain this phenomenon. Okay, electrons which are closer to the surface require less energy to escape compared to the electrons further from the surface. Okay, hence the electron closer to the surface are emitted at greater speed. So the electrons that deep below, deeper from the surface of the metal, so it will more likely suffer collisions and then emerge with altered energy and momentum. So the speed become less. Right? So that's why electrons closer to the surface are emitted at greater speed. Okay, now we go to question 4. A monochromatic light of wavelength lambda and intensity I is incident on a metal surface. As a result, photoelectrons are ejected at a certain speed from the metal surface. Describe the effect of using a monochromatic light of wavelength half lambda and intensity I. Okay, so we do question A first. For question A, the photoelectrons are ejected at a greater speed. Okay, so when the how we know, so from here in original the lambda is given, wavelength lambda is given, and I is the intensity, original intensity. So when we look at here, half lambda, that's mean the wavelength decrease. So when the wavelength decreasing, what happened to the frequency? It will increase and the energy will also increase. From this, we know from the formula, E equals to HF and F equals to C over lambda. So when lambda decreases, frequency will increase, and what happened to the E? So the E will increase. When the energy increases, so that's mean the photoelectrons are ejected at greater speed. Okay. Now question B. A monochromatic light of wavelength lambda and the intensity double, right, 2I. So wavelength remain the same. So what happened? More photoelectrons of the same speed are ejected. Okay, so this is the effect when we use the same wavelength and higher intensity. So more photoelectrons of the same speed are ejected. So number of photoelectrons ejected depends on the intensity. Okay, so the larger the intensity, so the larger the number of photoelectrons. Okay, for C, a monochromatic light of wavelength 2 lambda. So this time we increase the wavelength, original wavelength. So we double the wavelength. So what happened? So no photoelectrons are emitted if we double the wavelength. So if we double the wavelength, so that's mean we use different uh, energy of a photon, energy of a, we double the wavelength. Okay, so we use a different monochromatic light. Okay, so when we increase the wavelength, here becomes 2 lambda. So what happened? The frequency decreases and energy decreases. So therefore, no photoelectrons are emitted. So again, we can refer to this equation. Okay, now we finish part 1, topic photoelectric effect. So we are going to discuss part 2. The topic is work function and stopping potential. Okay, question 1. When radiation of wavelength 184 nanometer is incident on a metal surface, as shown in the figure below, the milliammeter reading falls to 0 at a reverse voltage of 1.32 volt. So what is the work function of the metal in electron volt? Okay, we are given wavelength 184 nanometer. Reverse voltage here 1.32 volt is the stopping voltage. And the work function is, we use symbol W. We are going to find the work function in electron volt. So the formula we are going to use is formula of the photoelectric Einstein equation, which is HF equals to work plus K max. K is the kinetic energy maximum. So F is C over lambda. And we substitute for K max, we can use the formula EVS. So EVS is given, and E is the 1.6 times 10 to the power of negative 19. Okay, so we substitute into the equation here, and also substitute everything into the equation. The Planck constant 6.63 times 10 to the power of negative 34. C is the speed of light. Wavelength we convert to meter. Work function is the question, what the questions wants is work function, and E and the stopping potential, and we get work function is 8.87 times 10 to the power of negative 19 joule. So the unit is in joule, because the work function, because we use the E here, and the stopping potential. And we also can answer the work function in joule. In joule here, we can convert it to electron volt. So to convert to electron volt, we divide by 1.6 times 10 to the power of negative 19. And we get 5.44 electron volt. So you can answer it in unit joule or in electron volt. Okay, question 2. Photons of x joule each are directed onto a photocathode with a work function of y joule. So a collector which consists of a plate is placed close to the photocathode. Write down an expression for the maximum speed of the photoelectrons emitted in terms of x, y, and m. So for question A, we are given x joule. So this is energy of a photon, which is hf, and the work function is given y, and we are going to find maximum speed. So we use symbol Vmax. Okay, we use photoelectric Einstein equation, hf equals to kmax plus work function. So the hf is given in terms of x and the work function is given in terms of y. So we substitute the two values into the equation and we rearrange the equation to get Vmax. So we put Vmax as a subtopic here. So x minus y, bring y to the left side, and half Vmax squared remain the same as at the right side, and the Vmax squared is equals to we cross multiply 2, so we get 2 times x minus y and divided by m. So square root Vmax is the square root of 2 times x minus y over m. So this is the answer for the maximum speed. Okay, next we go to question B. The stopping potential required to prevent photoelectrons emitted with maximum kinetic energy at an angle theta to the cathode from reaching the collector in terms of E, X, Y, and theta. Okay, so this time we're going to find the stopping potential, Vs. We use the symbol Vs for stopping potential. So how to imagine this? Because the photoelectron is not at right angle to the cathode. It is at angle theta. So how to imagine? So this is the cathode and this is the anode, which is the collector mentioned here. So the the photoelectron is incident at an angle theta. Okay, so this is the Vmax direction at angle theta. So we use the component uh, horizontal component to calculate the stopping potential. Okay, so the component of Vmax, we have V cos theta and V sin theta. Okay, we choose horizontal component because we are going to find Vs stopping potential. So we use horizontal component. So the formula for Kmax is EVS. Okay, and the kinetic energy is half mv squared. So we for maximum for the Vmax maximum, we choose horizontal component, which is V max sin theta. Okay, don't forget the square. So we have Vmax squared sin squared theta. Okay, so now we can cancel the 2 here. Okay, Vmax. Okay, Vmax. Before we cancel the 2, we look at the equation here. So we can substitute the Vmax into the equation from A into B question. So we substitute into here. So V squared, Vmax squared is 2 times x minus y over m. Okay, so we cancel m and we cancel 2. And we have we rearrange the equation to get stopping potential. So Vs is equals to x minus y bracket sine squared theta over E. So that's our answer for 2B, question 2B. Okay, now we go to question 3. The minimum energy required to remove an electron from the atom is 13.6 electron volt. Find the maximum kinetic energy of the ejected electron when a 55 nanometer photon is absorbed by the atom. Okay, we are given work function. Minimum energy required to remove an electron is work function. So we use symbol W. So this is understood as work function. And then maximum kinetic energy is Kmax, and the wavelength is 55 nanometer. So we use photoelectric equation. F is C over lambda. Okay, and we substitute all the value into the equation. So Planck constant is 6.63 times 10 to the power of negative 34. C is the speed of light. Wavelength we convert to meter, 55 nanometer convert to meter. And because work function is given in electron volt, okay, work function is given in electron volt, so the energy of a photon here need to be converted to electron volt. So to convert to electron volt, we need to divide by 1.6 times 10 to the power of negative 19. Okay, now everything is in electron volt. The final answer for Kmax will be in electron volt unit also. Okay, so the answer is 9 electron volt. Okay, next question 4. Silicon is illuminated with light of wavelength 220 nanometer and the stopping potential is found to be 0.85 volt. It is then illuminated with light of wavelength 160 nanometer and the stopping potential becomes 2.97 volt. Find the value of the Planck's constant H and the work function of silicon in electron volt. Okay, so we do question A first. Wavelength is given and the stopping potential is given. But we have two situations here. We have another wavelength, lambda, okay, we name as lambda 2. And the stopping potential for the second situation as Vs2, given 2.97 volt. Okay, so we have two situations using different wavelength of photon. Okay, so that means we form two equations. So we use photoelectric equation, okay, where F is C over lambda and Kmax is equals to EVS. Because Vs is given in the question, so we use Kmax equals to EVS, substitute into the photoelectric equation. Okay, now we form two equations. The first equation we substitute Vs1 and lambda 1, and the second equation we substitute Vs2 and lambda 2. Okay, W will remain the same because we have same metal. So the light is illuminated on the same type of metal. So that's why W remain the same. Okay, so for the first situation, H, Planck constant, that we are going to find. C is the speed of light and lambda 1 is 220 nanometer convert to meter. Then E is 1.6 times 10 to the power of negative 19 and stopping potential is 0.85 plus work function. So this is equation 1. So equation 2, we substitute all the same into the equation except for lambda 2 is 160 nanometer convert to meter and the stopping potential is 2.97 volt. Okay, so for the then we use simultaneous equations to solve for H. So equation 2 minus equation 1, so we get 5.11 times 10 to the power 14 H. Okay, and then the work function cancel and we get equation 2 minus equation 1. For the left side, we get 3.39 times 10 to the power of negative 19. So we solve for H, we get 6.64 times 10 to the power of negative 34 joule per second. So that's the answer. Now we go to question B. Question B, find the work function of the silicon in electron volt. Okay, so the work function, we use equation 1. Equation 1 is for silicon. So we substitute the H that we calculate in A. Okay, calculate in A into the equation 1. Okay, then we solve for work function. So the answer is 7.69 times 10 to the power of negative 19 joule. So be careful with this question because we are going to use Planck constant that we calculate in A, not in the constant list given. Okay, next we go to question 5. Okay, a graph is of stopping potentials Vs against frequency of three different metals. Okay, we have metal 1, metal 2, and metal 3. The F1, F2, F3 here is the threshold frequency. The x-intercept is the threshold frequency illuminated by light of different frequencies, F1, F2, F3. So explain why the gradient of the graph for each metal is the same. So the gradient is the same even though we illuminate with different frequency of light. Okay. Why? So we look at the photoelectric equation. HF equals to Kmax plus work function, and Kmax is equals to EVS. So we rearrange the equation here so that we get general equation for a straight line is y equals to mx plus c. So the y-axis will be vs and the x-axis is f. So we let vs as a topic, our subtopic here, vs equals to as a subject here, vs. Okay, and then we divide all the equation here with e. So now our equation is in the general form of y equals to mx plus c for the linear graph, right? For the linear graph here. So y-axis is vs, x-axis is f, the frequency. So that means the gradient will be h over e, and the y-intercept will be a negative work function over e. So we have negative axis, so it is correct when we make this line, draw this line longer, so it will get negative y-intercept. So it's correct to be minus there, negative there. Okay, so now from the gradient h over e, the gradient is constant. Planck constant is a constant value, and e also is a constant value. So the gradient is always constant. So that's why even though we use different frequency of the light, but the gradient of the graph vs against f will be the same gradient for all the three lights. Okay, so now if I plot here again, so if we draw the line longer, so the y-intercept here is equals to the negative work over e. So the y-intercept is negative. Okay, so the threshold frequency is the x-intercept. So the gradient will be h over e. Okay, now we go to question 6. Explain how the value of Planck constant can be determined from the graph of maximum kinetic energy against radiation frequency. Okay, this time we are going to plot the graph Kmax against F. Just now is stopping potential against F. So this time Kmax against F. So we refer to the photoelectric equation. So we put Kmax as a subject because we are going to compare with the linear graph general equation y equals to mx plus c. So y will be Kmax and the x will be f. So the gradient of the graph will be m, and the y-intercept will be a work function. Okay, and we can see here gradient also constant, which is equals to the Planck constant. So the graph we plot is Kmax against f, and it's a linear graph passed to the x-intercept, and y-intercept is the work function. Okay, so don't forget the origin here, and the threshold frequency x-intercept, and the gradient is h. So this is the graph Kmax against frequency. Okay, so now we have finished part 2 for tutorial 17, and see you in the next tutorial.